Good morning. This is officially the start. I've been waiting for people to show up. The class is pretty sparse right now. There's 3 people in the classroom. Hopefully it grows bigger. We're starting a new chapter, but I want to wrap up a couple of details from chapter 2 and see if there's any questions that might linger on chapter 2. And I want to show you at least one other thing that I didn't get a chance or didn't get much time to show. I will just talk about the fact that the chapter 3, which is all on the Z transform, I do have a Jupyter Python notebook pushed up there for that. I also have the PDF version of that pushed up. I have the set number 3 problems. I put those up, I guess, on Saturday after I'd collected all the papers into my holding area for grading. I'll probably put up some hints pretty soon, and the reason why I'm going to be really anxious on this assignment is, number one, it's probably one of the easier assignments because it's the Z transform. Why do I say that? Laplace transform, if you remember back to learning about that, and then introduction to the Z transform you've had in Signals and Systems already. They seem to be like the easiest digested DSP math food or whatever that you can come up with. It's just very clean, very, as a matter of fact. Now we're going to be adding layers to it here because we're going to be more sophisticated than perhaps in your earlier coursework, but still it's pretty straightforward. There's not really even a whole lot that you can do on the computer to model. But there are some tools, and we'll talk about those tools, and that's why there is a Chapter 3 Jupyter Notebook. When we finish this, though, we're going to be ready for the first exam. So I'm pulling up the calendar right now just so we can look at what's going on. This Z transform chapter, I should be able to get mostly through it today, but we'll have some more cleanup on it next Friday, October 5th. And then, of course, you'll be turning in the problems on the 7th. My intent, and in looking at the past, exam 1 has always been given on this date of the 12th. That's the nominally best time for me to do that. We can have a vote. I can overrule your vote. It's called a benevolent dictatorship, right? That's what I was taught. Actually, it was my choir director at my church who picked music for the groups that I play in. He always said, you can pick, but I can overrule. So I'm going to advocate for the 12th just because it will get it behind us. That means that I'll be pushing out the solutions from the old exams, 2 old exams. It'll be 2019 and 2021. I don't have a 2020 because I was on sabbatical during that fall. That was probably the darkest semester yet of the COVID reign, right? Things were totally with masking and everything, and I don't hardly know what happened then because I don't think a lot of people taught their class. I don't think anybody taught their classes in person except under special circumstances. But at any rate, I've got my 2 most recent exams that I'll put up there. And we'll talk more about that next week in terms of what it's going to be. But one of the things that I will probably bring in next week, but I don't have to, I don't have it today certainly, it will be, if we go behind the scenes here under the lecture notes, under the covers, we've looked at this before. I just have to focus my eyes on it. The cheat sheet that I want you to be able to have in your possession when you take the exam. Yeah, exam 1 tables. So I'll bring in a copy of this next week. The copier's working again. And I'll give you 1 paper copy, but if you want to get it printed off in the meantime, you certainly can do it. I just didn't ramp up on it today. I printed off solutions to set number 3, so I would have them here in class today, but you will be able to have that. and you'll be able to make up one two-sided sheet of your own study notes for this exam. This exam will be done in class, and Jack was going to ask me about it, but you didn't get here soon enough, so we're talking about it right now. Exam 2, just to review again, will be a take-home exam, and that will get kicked off on the Friday before spring or Thanksgiving. So, hey, we got the calendar here. We'll just look at it. I'll post that exam on October 18th, and then you'll turn it in by the 22nd, I believe is the date I generally have on it. And then when you come in and take the final exam, which I think is probably on the 14th, if I'm thinking right, that will be that will be in class again, but that will be open book, open notes. So this is the only exam where you just have limited material, but it's for your good, actually. I mean, there's less stuff to study right now, and why make it more complicated? Because whenever I have an open book, open notes exam, there's just more flailing around of stuff in general. So I think this will be good. So like I said, I'll bring this in next week, and if you want to make a copy in the meantime, that's fine too. So before we get started on Chapter 3, I want to see if there's any questions, any wrap-up questions that anybody might want to ask me about the Fourier transform of sequences, frequency response, which is the Fourier transform of the impulse response, working with difference equations. I want to look at one of the things that's in the appendix of the notes, and then jump back to Jupiter for a moment or two, and then start in 3. So any questions on any things hanging over? Okay, so I'm going to go look at this section that I wrote called DTFT of special sequences. And this first example is the one that I just want to look at briefly. We will kind of bump into it again when we look at sampling theory, but I thought it's kind of a cute example of something that also is a curiosity. Does something like this exist in the discrete time domain? You learn when you learn Fourier transform theory, you learn about you can have an impulse train in the continuous time domain, and then remember its spectrum is an impulse train in the frequency domain. Do you remember that? If you don't remember it, then this is not quite as impactful, but it's a very special transform pair that we have. And I'm just going to go the distance here and open up another file, jump ahead for a moment. We're probably going to do the FFT before we do this chapter, but there is a section in here that we will be coming to under periodic sampling. And the Fourier transform pair I'm thinking of is if you've got an impulse train in the time domain, continuous time domain, that becomes an impulse train in the frequency domain. I mean, we'll be reviewing this again when we do Chapter 4, but if you don't remember that, I'm not totally disappointed, but you're going to want to get your brain wrapped around that again. It's kind of a it's a special transform pair, and this is Fourier transform trivia, but there's 3 signals whose signal and transform are of the same mathematical form. And when I taught as a PhD student at Missouri S&T many years ago, the faculty that taught signals and systems had this as a exam question, or they talked about it as being kind of like a trivia question. So the first one of the 3 is trivial. If you have a signal that's 0 and you Fourier transform it, you get 0. nothing exciting there, but it is true. Fourier transform of 0 is 0. Fourier transform of an impulse train in the time is an impulse train in frequency. This is now under the Fourier transform in the limit concepts, and that's this theorem right here in the omega domain, which is what we're going to be using when we do chapter 4. And then the third signal, does anybody have a guess or remember ever being told this or learning? It's not a real common signal in electrical engineering, but it still is useful. It's a Gaussian pulse-shaped signal in the time domain is a Gaussian pulse-shaped spectrum in the frequency domain. Is that, you know what I mean when I say Gaussian? It's the bell curve. It could show up in Fourier optics, and that's where I had definitely seen it. Fourier optics is not a one-dimensional signal processing scenario. It's generally two-dimensional or three-dimensional. Fourier optics, though, would be related to the intensity of, say, of a light pattern, and then the transform of it you could get after going through an aperture, and then you get something called Fraunhofer diffraction, something you probably have never heard of either, but maybe you have. But still, I don't want to get really off into the physics part of it in optics, but a Gaussian pulse transforms to a Gaussian pulse. That's kind of the interesting story there. And there is a modulation scheme in COM theory called GMSK, stands for Gaussian minimum shift keying, and it typically will use a Gaussian pulse shape in the time domain to modulate a carrier, and then it ends up being a Gaussian shape in the frequency domain. And why is that kind of interesting? Because GFSK, Gaussian frequency shift keying, is what Bluetooth uses. And we all use Bluetooth. We don't maybe realize it, but it's part of our device interfacing, right? Bluetooth is a PAN standard, personal area networking standard. Probably too early in the morning to get you excited about trivia. Okay, so back over to this. This is just the discrete time version of the impulse train. So it says we'll put a discrete delta at every mth sample, and then if we Fourier transform that, we take the Fourier transform of the sequence, and I've simply dropped it inside of the definition or of the Fourier transform, and then we've got a delta function floating around inside of here, and the delta function is going to fire at every mk when n is equal to mk, so it changes this sum into a sum of this form, e to the minus j omega mk. And we don't really have the exact tools for doing that right now, but there's something called the Poisson sum formula, which shows up in Fourier analysis. It also shows up, I think, in province stats. You might bump into it, but from that you can establish that this is going to be an impulse train in frequency. An alternative way of doing that, though, is to work from the continuous time domain and then sample and recognize that we have a discrete time signal that fires every m samples, and this is what it would be in the continuous time domain, and then use that theorem that we were just looking at from chapter 4 to say that the spectrum of it is going to be a sequence of deltas. So that brings us down to the blue box here, which just says Fourier transform the deltas, and you get an impulse train in frequency, which looks like this. What I'm going to do to try to at least say what types of things that you might try to do if you're looking at this math saying it just seems too mysterious to me. Why could this actually be? you can always go to a tool and try to simulate this, try to model it and just see if it represents it properly. So let's take a look at that. Since I haven't done this for a while, my brain was thinking this morning about how the best way might be to do this. So I'm going to go to the end of this chapter 2 notes that we had been looking at. I'm going to add a cell down here, and I'm just going to say, how can I do this? I'm not going to be able to do the doubly infinite series. I'm just going to do a long sequence. So I'm going to take and create 100 ones, and then I'm going to use a function that we'll be learning about in chapter 4 called upsample. And I'll let you see what the definition of that is. Upsample takes the input signal and it inserts L-1 0 samples between each input sample. This is called, like I said, upsampling. We'll be learning about this later. So I'm going to put in X, and then I'm going to put 10 in here, just so I'll upsample by a factor of 10. And then I'm going to attempt to do a stem plot on that, and I may have to shrink the length down on this. Yeah, I'm going to plot less values out of this. So I'm going to go 0 to 100. So you can see the upsampling has indeed worked. I've taken a bunch of ones and I've stuffed zeros in between. So now I've created, as a simulation, a periodic impulse train where the period is 10 samples. And if I zoomed in on this further, which I could do here if I wanted to, 0, 15, let's say. I could just verify that there are indeed 9 samples in between, and every 10th sample fires. Look good? So now we have a waveform. Now what we can do is we can use, and this is talked about in the notes, we can use the freq z function to approximate the spectrum. If we just take the freq z function and put the signal in place of the b vector and put 1 in for the a vector, which is the denominator, we can approximate the Fourier transform. So I'm going to create a frequency axis that goes from 0 to 0.5, and I'm going to let this be 1 over, I don't know, I'll just pick not a power of 2 for the spectrum, but I'm going to do 1 over 5,000. And then I'm going to go capital Y equals signal. I'm going to use freq z. And then I'm going to put the signal in there, which is y. I'm going to put 1 in for the denominator. And I'm going to make my frequency axis, which in the freq z function has to be in terms of little omega. So I take 2 pi times f. And now I can come down here and I can just plot it and see what I've got. So I'm going to use that frequency axis f, and I'm going to use the absolute value of capital Y and see what I'm getting. This is not perfect because it's a finite duration, so it's not a perfectly flat impulse train, and it does have a scale factor of 100 on there, which has to do with the sample spacing and the period. But all I'm really interested in is demonstrating to you that the period was 10 samples, so 1 over the period should be the spacing of the spectral lines. If we were to go back over here to the notes, we've normalized 2 pi away, so every nth sample is what fired on here, and then the spectral line should be at 1 over m, or 1 over 10 in this case. Does that make sense? I'm not saying this is rigorous, it's just a simulation model, but you are seeing that there's some side lobe structure in here, but it's still trying to produce a strong spectral line at those harmonics of 1 over the period. And if I was to change this over here to be 5, let's say, run it again, now it's every 5th, run the spectrum estimate again. 1 over 5 is 0.2, so it's doing that. If you don't like this, I don't know what to say. If you just like pure theory, you just got to stay on the math side of it. But I like being able to jump over and just checking out my intuition and just doing a numerical calculation to see what's going on. And a lot of times when you're dealing with signals and signal analysis, somebody gives you a test vector captured from some capture, you do analysis on it, you look at it in the time domain, you look at it in the frequency domain, and if you see periodic spectral lines, they may not be of uniform height like these are, but still it starts making you think about what's going on with this signal and how do things get reproduced like this. So I find that interesting. And it's comforting to know that what holds in the continuous time domain also holds in the discrete time domain. So we'll bump into this again and we'll see how that goes when we bump into it again. The last thing I wanted to do in here is we were talking about last time how we were looking at 2 sinusoids, one at a frequency, normalized frequency of 1.0, or no, 1/10, and the other one at 1.5 over 10, which would be on the normalized frequency axis 0.1 and 0.15. This spectral plot up here is just one of the 2 sinusoids. I didn't put them both in here. Why don't I just do that, since this may have been confusing last time. I'm again using freq z to estimate the spectrum, the Fourier transform of a sequence, and like I said, I do talk about that in the chapter 2 notes in the Python section. So I'm just putting my signal in for the numerator and just putting in 1 for the denominator. And in this case, the amplitude of the higher frequency sinusoid is 2 over 50, and the original sinusoid is 1. So this is a linear scale, but you can see that the weaker sinusoid is sitting right down below here as a little spike, and then the one at plus 0.1 normalized hertz is the big one. And then this is just plotting a few cycles of all of that, which I did just sort of for the fun of it. I could change this to be 0 and put in 0.5, and then I'd just be seeing 1 period of it, which is more along the lines of what I'd typically want to see. I had done it that way so you could just see how the spectrum is always periodic. Remember, that's a property. But in this particular problem, the idea is if the sinusoid is now windowed, we don't have a long capture window. Here we've got 1,000 samples, but suppose in reality we're not going to have 1,000 samples. We only get a few samples. In this case, I said 100 samples, maybe in a data acquisition system or some scenario where you have to quickly capture some intercepted signal and then quickly take those few samples and see what's going on in the frequency domain. So that's putting in this window, and that's what was done here. A rectangular window of M gets multiplied times the sequence, and then I also have a second type of window called a Hanning window that gets multiplied times the sequence. And I thought I had plotted these last time. I'm taking more time now, but I think it's probably worth it. So let's just plot. Rather than the 50 dots, well, I could do it that way too. It's only 50, so I'm just going to plot it. Understand that connecting the dots is not totally legal, but it sometimes makes things easier. So do the rectangle 1. Okay, I guess I could use stem on this. Now I'll plot the second one on top of it. And that's going to be the other window that's applied, the Hanning window. And I should have used plot because stems don't overlay very nicely on top of each other. So now you can see what the idea of the window is it's tapering down the ends of the signal capture. So suppose we capture 100 samples, but if we just abruptly end, start with a transient where it turns on instantly and end with a transient where it turns off, we create a lot more side lobe structure in the Fourier transform. Whereas if we use a window, we shape it so that it doesn't have that abrupt start and abrupt end to it. And that's what the Hanning window does. And here I did the spectral plot of it, and this was done last time, where I'm just going to use freq Z again all the way through. And what you see is that with the rectangular window, you have all this side lobe structure. It's down only around 18 dB from the main lobe of the strongest signal, and then it starts to fall off at about 6 dB per octave, which is not very fast roll-off. And for the case of having a near-in sinusoid that's just 1.5 times the frequency of the strong sinusoid, you can see here that it's getting washed over by the strong signal side lobe structure. If you were processing this as a radar return, or again intercepting a signal, and there were two different targets out there, let's say, one is strong, one is weak, would that blue be good for you? I mean, you wouldn't be able to see the weak signal out there, right? So windowing in this case allows you to reveal something that's hidden if you use only the rectangular window. We're using just 100 samples at this time. If this was to change, obviously the game changes. If I was to take this up to 500, we'd have more in the time domain. And then you can see in the frequency domain, you're starting to be able to resolve it. But I think the blue is still, well, the blue is washing behind it some more. But going in the other extreme, if I went down to only 50 samples in the capture, that doesn't look, if you look at the raw data, that you say, that's not hardly anything, right? It's a number of cycles, though. It's not 0. And then process this down here. Oops. And there it is. No chance of seeing it in the case of the rectangular window. With the Hanning window, because it has a wider main lobe in its transform, there still is a little blip there from that other return, the other signal. Is this kind of exciting, or is this like no one cares about this? Well, think of it the other way around. Suppose the police radar are seeing 3 cars coming down and their gun is pointed at 3 cars, do you want to be hidden from the other 2? You'd probably say, yes, I don't want to be detected. But, you know, if you both have nice reflection off the vehicles and one is going obviously faster than the other, that's probably the one that would get the ticket if it's over the speed. I'm just trying to create a scenario, come up with another idea. Can you dream up another reason why you'd want to process the data in a certain way? This is kind of the limit though. 50 is really tiny. And of course, if I move the sinusoid out further, it will have a better chance, but still the roll-off rate is so tiny here that it's the frequency of the other guy, which would be the faster car that might be weaker coming from a greater distance away. It's still going to have to move up in frequency a lot to fall into the roll-off of the rectangular window. The number of windows that are out there is just, it's pretty phenomenal. It's not, people have been exploring windows for a very long time, so I think they're in here. Yep. So notice what I did is I went into scipy.signal and then I typed into a sub package called Windows, and here is just a few of the windows that are supplied natively with scipy.signal, but there's probably at least 5 times this in existence because people have been messing around with Windows for a long time. And then there's general windows, like they say, general Gaussian, cosine. People have their name on these too. Tukey is a guy, Taylor, Parzan, Nuttall, Kaiser, Han, Hamming. Those are all people's names. Blackman and Harris, people's names again. I've got a book. Maybe I'm going to have a giant book sale, giveaway of books at the end of the semester. I'm going to start giving some away earlier, I think, too. So it's intriguing, right? If you're interested in this stuff, these windows show up on our oscilloscopes for doing the FFT analysis for a time domain capture to change the resolution capabilities, and they show up in the design of things too, design of filters. And that was really the next topic in here. I just wanted to quickly say that we'll eventually be talking about, and you'll be trying this out, how you, besides windowing data, you might want to use this to design an FIR filter. Remember, the ideal filter has the sinc function shape, which goes to plus and minus infinity. If we just truncate it, that's a rectangular window over that sinc function. If we taper it down, so functions that are available in scipy.signal are FIR win, and you get to specify optionally, and MATLAB has this too, you get to specify optionally any of the windows that are available. Now I have a package a sub-package in scipy.signal which specifically does filters. It's called the FIR Design Helper, and it has got certain types of filters. It has Remez, low pass, high pass, band stop, and then it has Kaiser, and it has an interface that's a particular type of interface. We'll look at that probably later in the project or something, but just using this simple interface that's available in scipy.signal, I created Boxcar, which is the rectangular, and Hanning, or Hamming, I guess it is. That's the default, I think. So those two are created here, and then I'm going to get the frequency response or the Fourier transform of those two down here. And you can see in creating a windowed FIR design if you don't apply any window, you just truncate that sync function and say I have to truncate it and then slide it to the right so it's causal, right? Because a double-sided sync function is also going to have impulse response for negative n, so truncate it and slide it to the right. You get really high side lobes, and that's what we're seeing here. This is not a very nice looking filter. This is just like the windowing problem we were looking at for the signal capture. It rolls off only at 6 dB per octave, whereas if we use a shaped window, like the default Hamming, I believe it is, it's a little bit wider in the passband because of that window, but the side lobes drop down and stay down and actually go down even further. So if we were to look at this down to 80, you'd see that they don't drop off infinitely fast, but they do different things. And if I was to put, I'm pretty sure it's Hamming. There's the hand window or Hanning window. See, it drops off more rapidly. I think this has got 18 dB per octave roll-off rate. And the main lobe is down, or the first main lobe is down like 45 dB. So they all have slightly different properties to them. Any questions or any comments? Those are the coefficient sets. I just ran them in the time domain to see what the outputs look like. They all have a transient response. Those of you taking the lab will be designing some filters in lab number 4, and then once you get the filters designed, you will use this package, coefficient to header, which converts the filter coefficients to C header files, and then those header files can be imported or included in your C source for the microcontroller, and then you can apply these filters to the signal. Okay, I'm going to move on to the next chapter actually. Thinking there was one other example in here, and you can take a look at this one on your own. The unit step sequence is not as simple as you might think. It's got some other terms in it. And its spectrum, it's just an ugly spectrum. I don't really try to go with the unit step and do anything with it in the frequency domain. In the Z domain, we're going to be using it all the time though. So just a quick overview. We're going to start off with the bilateral Z transform, which means it's designed for two-sided signals and causal and anti-causal systems modeling. It's the full-up tool that most people use in DSP. A special case of the bilateral, which gets talked about at the end of this chapter, is down here, unilateral. And the unilateral transform is useful for solving initial condition problems. Just like when you learned about the Laplace transform, you actually were taught in circuits and systems the one-sided Laplace transform, because you learned in circuits in particular that if you can take your differential equation to the Laplace domain, then you can solve for the transient response given the initial conditions and so on. It's the one-sided Z transform that provides that capability in the discrete time domain. But most of what we're going to talk about is the two-sided or bilateral transform. Along the way, the book used to teach you contour integration for the inverse Z transform using Cauchy's integral theorem and residue theorem. They took that out to provide space for more things on sampling theory, multi-rate sampling, which is a really good thing. I left it in my notes because it's kind of like the history of my teaching this class. So it's in the notes. We're not going to go through it, but it was commonly introduced 20 years ago in all DSP classes. So do things change in engineering? Yes, they do. I mean, originally when this came from a deep theoretical topic for only graduate students, all this stuff was in the books, and then they gradually dialed it down and brought in some newer topics. So the way it gets presented in the Oppenheim and Schaefer book is it's viewed as a generalization of the Fourier transform. And the Fourier transform was for a bilateral sequence, something that could run from minus infinity to plus infinity. And this is just like the two-sided Laplace transform then that you would see for continuous time systems if you had learned that from the beginning. But it's safer and gets you right to the problem solving that you wanted to do in circuits if you go with the one-sided transform. So here we're going to expand our horizons and see the bilateral transform. Advantages of it are it converges for a wider class of signals. The notation, much easier. We're going to have Z instead of e to the j omega. And I don't know about you, but Z is a lot easier to write. Manipulating equations around with just Z or Z to the minus 1 is going to be a lot easier than writing e to the j omega. And we'll have the ability then to substitute in later as long as we know the transform exists. And we'll talk about that in a little bit here. And the third thing is that it allows the power of complex variable theory to be utilized. That was certainly true in the olden days when Cauchy's formulas for integrating, doing contour integration were introduced in these courses, but now it just sits behind. It's sort of hidden in the shadows. It's not seen anymore like it was. But it's still the power of complex variable theory, which, because I was interested in exploring more math when I was an undergraduate student, I took complex variable theory when I was transitioning from a BS degree to an MS degree. And I did, my BS to MS degree was pretty much the way it's now done here at UCCS, where you can be entered in before you actually graduate. And what's that called again? Some of you probably know what I'm talking about.
It's called the AMP, it's Accelerated Master Program.
Yeah. At my school, Michigan Tech in Upper Michigan, it was called the senior rule is what it was called. And what it was is, as a senior, you could start taking classes already and apply them to your master's degree before you even graduated. So that's what I did, and that's how I ended up taking complex variable theory from the math department. So what is the bilateral Z transform? It's defined simply as a double-sided sum over a sequence, and instead of the e to the minus j omega, we now just have Z to the minus n, where Z is a complex variable. So it looks nice and wonderful. I mean, wonderful in the sense that you know that a geometric series sum formula is going to be used. If you think otherwise, you're forgetting the fact that I made this promise effectively, that the geometric series sum formula would be used over and over again, and it was worth your time to invest in manipulating it around. So the operator notation is a script Z, just like we use a script F for Fourier, and then on the right-hand side, it transforms x of n to capital X of Z. And in the Z domain, we have a function of a continuous complex variable Z. And that comes about because in the definition of the Z transform, we end up insisting that the Z transform definition be absolutely summable, and then that ensures the continuous function in the Z domain. However, we do admit a few different types of signals that are special, and that then breaks this property of continuous, and we'll talk about that, and we'll see how that allows representation but doesn't give you all the benefits. It's kind of like you have, trying to think, a contract where this follows from that and you get all the benefits, maybe like a life insurance policy or something. But if you have something weird going on, you don't get all the benefits, you just get some of them. And that's kind of what happens here. Mostly, though, it is continuous within something called the region of convergence. And that's what we'll be getting into very soon. So bilateral transform. The unilateral transform uses a slightly different notation. Rather than saying it's capital X, it's calligraphy capital X in the notation of the book. And the sum runs from 0 to infinity rather than minus to plus infinity. So for boundary value problems or initial condition problems like you see in controls and in circuit theory, where you apply a signal at t is equal to 0 or n is equal to 0 in this case, the one-sided transform is sufficient, and it allows you to have a way of managing the initial conditions. Right now, at this point in the class, the only way that we have for handling initial conditions in a system model is through the classical solution technique, which I dragged you through, and I'll see how you adapted to it in the homework problems. I'm guessing not every one of you tried the classical solution and the initial conditions and all that stuff. You opted for trying to make it work with Fourier or something like that because you're just so engineering-like, path of least resistance. I don't want to learn anything new if I don't have to, even though I've got the screwdriver here and I'm screwing two boards together, which means, I'm putting the pressure on you to try to learn something new. But so it goes. We're now on to the Z transform, and when we get to the unilateral, we'll see how that works. But we're not going to go off and do all the crazy things that you do in circuits with initial current on inductors and voltage across capacitors. Don't want to do any of that. Don't have a need to do any of that. If you want to study that on your own, you certainly can, but that is where that tool set resides, in the one-sided. We are interested, though, in the connection of the Fourier transform. So if we let Z be R e to the j omega, then we have a polar form representation for the complex variable Z. And if we plug that representation into the Z transform, then we can see that the Z transform effectively is giving us x of n times r to the minus n. And that r to the minus n you can think of as being a weighting function. And that weighting function is what actually controls convergence properties. It would make a sequence that doesn't converge in the Fourier transform sense converge in the Z transform sense because that weighting is on there. And hopefully that, I'm not explaining the intimate details, but doesn't it make sense that if you can control a sequence by multiplying it by some other sequence that maybe makes it damp out faster, that the series would converge? Now, what does it mean then when we have that? It means that it won't track. The Fourier transform is only going to match the Z transform when r is equal to 1, because then that factor is unity and it doesn't alter the signal at all. And that also brings up this idea that when we have a Z transform x of Z, which is defined over the entire complex plane, and if we set Z equal to e to the j omega, which is the unit circle in the Z plane, then that is where the Fourier transform comes from. So I've alluded to this maybe once earlier, actually in the intro lecture on that demo with the pole zero plots, which I never really fully finished showing you. That was in the Pluto notebook. But I can come back and look at that at any time, and I sort of decided I won't do that now because I don't want to get you more confused. But this is a more powerful way of thinking of the Fourier transform. Then we have the Z transform, and we take a cookie cutter. I mean, if you don't bake cookies, in my household, I'm the person that bakes the cookies, and I have a cookie cutter that's round shaped like this at Christmas time that I use for making cookies. And so I cut out in the unit circle, and I cut that out, and then it's a circular shape, but I lay it flat in a strip, and then I have the Fourier transform. So, you know, this point right here, Z is equal to 1 corresponds to omega equaling 0, and then this point over here e to the j pi, which equals -1. Which is omega equals pi. So that trip around the top is actually the fundamental interval that we've been looking at. This, if we travel like that, that's 0 to pi. That's what we get when we slice the top half of the unit circle out of the z-plane. That's sound cool? A long, long time ago, when Dr. Ziemer, who was my dissertation advisor and mentor and started off being the department chair here, said, you try to explain that to students that are cold and they're not going to get it. And I've been learning over the years that it doesn't work as quickly as I think it should work. So if you're still fuzzy on it, that's fine. Try to get adapted to this idea that the z-plane, when evaluated on the unit circle, is the Fourier axes. And I know when you studied the s-plane, you caught on to that, I'm guessing. The s-plane is from continuous time, and if you look at the j omega axis, it's up there vertically. So quick review of that. Omega equals 0, and sigma, the real part in the s-plane. Remember s. The stuff I put up there in the corner, that should be vaguely familiar. If you're taking control systems, it should be probably already really familiar because you're probably using it a lot already. But so we're just now in the z-plane, and we just have a different view of things for the discrete time domain. So this bullet down here just takes you around the circle and points out the equivalencies. So the next big discussion here, which is going to lead to some of the first hurdles in getting into the z-transform, is convergence. So we call the region of convergence the region in the z-plane where the z-transform converges. It's just a fact of life in the z-transform that it does not converge for all sequences, does not converge over the entire z-plane. The thing that I think is probably the hardest to grip on the Z transform is that because when you think about sequences in series and properties from mathematics, you tend to think that everything has to converge everywhere to be good for anything, and that's just not the case at all. I mean, think about the S-plane. Do you have things converging for the positive S-plane? Remember, you can't have poles in the right half S-plane for a causal stable system. So we have that in the Z domain as well. I think you're just kind of, since I'm old and retiring from teaching now, I'm going to have to fade out on having to go through this stuff, but just things pop into my head like when you're growing up in this stuff, you have these flashbacks where you think, I think I have it, and then you go a little bit step further, and then you start to have a flashback like, I'm all confused again, I don't know what's going on. Do you ever experience that? Be honest, do you ever experience that? It's normal, it's just part of growing up, and I think, the sad thing is, I'm talking about our physical lives, and when you get older and older, pretty soon you can't walk without falling down anymore, and if you were a baby, you were trying to learn how to walk, so everything goes up and comes back down again. I'm not excited about that right now myself, but I think, that growing up at least, you get more and more confidence as you get more experience with things. So region of convergence is the term that's used, and ROC, or if you want to pronounce it as a word, it's called the rock, except it doesn't have a K on the end of it. So you can still call it rock though, right? ROC, I'm fine with it either way. So the type of convergence we're looking for is the same convergence we were seeing with the Fourier transform. Must be absolutely summable. So absolute summability says this. We take the argument in the Z transform definition and we put absolute value signs around it, and if we take our Z and write it as R times e to the j omega then I put the absolute value signs around it, and I just get R, or the magnitude, the radius, in the Z plane. So that ends up being the controlling factor in the region of convergence, and trying to get absolute summability out of this x of n times r to the minus n, and the absolute value of that. I want to go off on the side here and do something that will come in handy a time or two as we move along here. If you have two real numbers, two complex numbers, doesn't matter. We have something called the triangle inequality. Remember that from calculus somewhere? It's a property that gets talked about in complex variable theory, but just to review what that would be. That's the triangle inequality right there. Sometimes this will be useful and sometimes not. I'm not going to use it here immediately, but it just popped into my head because as I was reviewing the solutions, I saw triangle inequality for one problem or another where it was useful. When I took my advanced calculus / real analysis courses in getting my doctorate, we had to do proofs on the board, we had to do proofs on paper, but triangle inequality was one of the fundamental inequalities which we could use to prove something or show something. And it comes to mind here because we do have a doubly infinite sum of values in here. So, but the sum is not inside, so that's why the triangle inequality doesn't apply immediately to this problem. But at any rate, we're going to go look at an example. So, first off, what does the region of convergence mean? Well, one of the things that you get from right here is that convergence is not going to depend upon on a particular value of z. It's only going to depend on the magnitude of z. And the magnitude of z is r. So a true statement is that the region of convergence is going to be some annular region. If it works for a particular value of z, it's going to work for anything that has that same radius. And this is the annulus or ring for the region of convergence. So this is just a general form of the region of convergence. It has an inner radius and an outer radius. It's possible, my pen will keep working. Possible that the radii there could either shrink all the way to 0 on the inner radius or go all the way to infinity on the outer radius. We're going to have a whole bunch of properties relating to what it constitutes a valid region of convergence, but one of them is it has to be a connected region. And what connected region will mean is that it can't be an annular region here, and then it can't be another annulus that's further out, because those aren't connected regions. They have to be connected. It'll end up being the intersection of regions, if anything, and if the intersection of two regions is an empty set, then the Z transform doesn't exist anywhere. We'll see that. Something we're going to get to describing more later is that if the unit circle is contained in the region of convergence, then the Fourier transform exists or also converges absolutely, because the unit circle is when r is equal to 1. So that's really good news. That's the news that tells us that if we're studying in the Z domain and we happen to see that the region of convergence contains a unit circle, we have that the Fourier transform exists. If it's a system, in other words, an impulse response being Fourier transformed, if the absolute sum exists, then from our theorem on stability for LTI systems, that will mean that we have a stable system. So we're going to be able to, we can conclude even already that if the region of convergence includes the unit circle and it's the impulse response that we're Z transforming, then we have a stable system. So that will be the requirement for convergence. If we're talking about a causal system, we'll get to this later, all the poles and zeros have to lie inside the unit, or all the poles have to lie inside the unit circle, and the region of convergence will be the exterior of a circle of some largest pole radius. Then that will include the unit circle. So that will form the dual theorem to what you learned for continuous time signals and systems, namely that the poles must lie in the left half S-plane. For the Z domain, the poles must lie inside the unit circle for a causal stable system. Sound fair? Rules, 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 I know, but rules that make sense is what it is. We're just touching it right now, so don't get worried. I'm going to be talking about it a lot more. So there's some other properties that come out in the Z-transform. In complex variable theory, the Z-transform is what's called the Laurent series. And when I took complex variables, we spent a lot of time on Laurent series, and it helped me come to a better understanding. And if you can believe it, and I think you can, I hadn't even studied the Z-transform. I didn't do that until I was a graduate student. I didn't take discrete time signal processing until later in my life because it really wasn't taught that commonly. It was only for graduate coursework, so I never saw it until I was a graduate student. But I did take complex variable theory, so Laurent series were familiar to me, and then when I saw that they were connected to the Z-transform, I'm like, this is, wonderful stuff. Things about life and studying in engineering school, you can learn something in math and you just think it's pure math. I'm never going to do a thing with it. It's not going to be all that useful. Or if it is, it's going to be infrequent. You're studying engineering, this is what you want to do, but things do connect together in certain areas in certain times. So taking an advanced math class for me was always kind of a trip in the theoretical domain of just expanding your mind, and I never had ultimate expectations that I would do anything in engineering with it. I just wanted to learn more foundations. But when you get little paybacks like that, it's very worthwhile. It makes you more excited about this stuff. Isn't quite so crazy, but trust me, I live in the hallway with the mathematicians. I know many of them do things that are very practical, but I know many of them do things that are extremely theoretical. So I can't connect with them as well as I can with the other, the faculty. Any experiences you had as an undergraduate with a faculty member in math? You want to talk about it? It's like, I have respect for what they do, but I'm like, I'm not really excited about this. It's just too abstract for me. And what we do compared to the average person on the street, we're too abstract for them too. Just tell me my car works when I turn the key or press the button and I can go. That's all I want to know. Okay, so other properties though Laurent series brings is what brings the fact that not only is a continuous function, all the derivatives are continuous functions within the region of convergence. And if we go sample around on the unit circle to get the Fourier transform, all of its derivatives are continuous. And that also brings about the stability idea. And Bluetooth is intermittent here. Now there are certain sequences like the sinc function sequence that we had for the ideal low-pass filter, or cosine, which were not absolutely summable in the Fourier transform case, but we could allow them in Fourier transforms in the limit. Sort of a sad note, but a true note here is we can't go ahead and evaluate the Z-transform on the unit circle to get those Fourier transforms because it's not going to work. And that's one of the reasons why when we see U of n transforms to 1 over 1 minus z to the minus 1, and then we say, okay, let z do that. Then you get crazy and you say 1 minus e to the minus j omega. I say no, you can't do that. And that was the very last thing I was looking at over here, and I was looking at the idea that if you have a unit step function, try to evaluate its spectrum. which is what I did here in this appendix problem, I get a term that looks like 1 over 1 minus e to the j omega, but in the Fourier transform, the limit idea, I have to add in this additional term, and the z transform does not bring that into the picture at all. Don't ask me to try to explain it. I just accept it as it's because we don't have convergence. And the reason why we don't have convergence, go back over to here, the reason why we have to throw out that notion that we can get the strict converging Fourier transform is, and we're going to see more on this as soon as we work this first example problem. If we look at 1 over 1 minus e to the minus 1, that the 1 minus e to the minus 1 has got a root at z is equal to 1. In other words, that's a pole. So we have a pole sitting at z is equal to 1 in the z-plane, and that's a point of infinity. The z transform doesn't exist, so there's no region of convergence on the unit circle for this u of n function. We'll be exploring more of that later, but that's fundamentally why we can't do this, because the Fourier transform does not exist for u of n, and we know that already. I mean, we know when we did the absolute sum of that, it goes off to infinity. So this little thing I did with the substitution there doesn't work in all cases, so you just got to be careful. I remember, many years ago in the S domain, just thinking all I got to do is replace S by j omega and I have the frequency response. I got zapped by that on a few occasions, and you maybe did too. So just be careful is really what I'm saying here. Usually when we do a z transform, we're going to find it converges to a ratio of polynomials inside the region of convergence, p over q, and the roots of the polynomials p are going to be known as the zeros, and the roots of the denominator polynomial q are going to be known as the poles. So now we're going to take a simple sequence and just go through the exercise of finding the z transform. So we have kind of our classical problem, a to the n u of n. We've seen this a bunch before. Plug that into the definition. We have a sum from minus to plus infinity, but we have a u of n, so that immediately makes it start at n is equal to 0. And then in anticipation of this geometric series that we're so acquainted with, we'll just group the powers together. We have a and z to the minus 1 all raised to the nth power. And then we know that this series converges as long as the ratio, just going back to what we learned when we were studying, first reviewing these guys. This is the ratio in the geometric series, and as long as it has magnitude less than 1, then we have convergence. So we're absolutely summable. Fourier or z transform converges as long as magnitude of z is greater than magnitude of a. So strictly speaking in notation, we use a set theory notation with the curly brace and the colon to say region of convergence is the set of points z such that magnitude of z is greater than magnitude of a. A slang notation would just simply be to write it as something like that. Magnitude of z has to be greater than magnitude of a. And the z transform is 1 over 1 minus a z to the minus 1. And multiplying through to get positive powers of z, we have z over z minus a. So immediately have down here, that the poles and zeros of the Z transform are a 0 at 0 and a pole at Z is equal to A, and right here I've shown it for A of real value. So it could be anywhere out here. In that case, it'd be imaginary, so it's got a J times A on it rather than just A on the real axes, but it's still valid. So it's the exterior in this case, because that's what our geometric series sum formula led us to, magnitude of Z greater than A. And it includes the unit circle. So we have, if this was an impulse response for a system, this would be stable. If this was just a signal, it would have a Fourier transform that exists because the ROC includes the unit circle. So it's exciting. I say it's exciting because it all works, it plays together. This idea of associating the region of convergence and then with including the unit circle is wonderful. The other wonderful thing is you cannot converge at all on the circle of radius A because that's where the pole sits. But the theory also says that the geometric series won't sum for A less than, or for Z, magnitude of Z less than A either. The sequence diverges at that point. I guess I have to go back to, I'm going to go back to a notion, a camping notion. What are poles and zeros? Well, zeros are, to me, like stakes when you're taking your tent and staking it down, right? The body of your tent, and then you have a pole. I mean, a modern tent has, at least I have a solo backpacking tent that I really like because it's super lightweight, but it's got poles that plug together and are flexible. But in the olden days of a circus tent, that's what I'm thinking of. A circus tent is something that's a pole that goes up very, very high. The notion, though, of a pole in a tent has to be abstracted to say it's a pole that goes to infinity. It goes up really, really high. So that's not quite, the pole that you think of in a tent, but it's the abstraction of that. So pole is something that blows up at its location. It's something that's sticking straight up to infinity in the Z-plane. And a zero is where the function, if this is a surface, and I always think of the idea of a rubbery surface that's stretched out over the Z-plane and we're tacking it down, and then at the pole we're pulling it up all the way. So we have a rubbery surface that's tacked down at Z is equal to 0, and it's going up to infinity at Z is equal to A. In a later chapter I have three-dimensional pictures of this that just show you what it looks like. You can just imagine it, though, as being a special tent shape. I mean, 10 poles and that sort of thing. Any questions on this? Do you love the do you love the geometric series usage here? You just get to keep practicing it so you don't lose sight of it. It's just, I don't know. I like it. I'll be talking more later, too, that for signals, we always have an equilibrium between poles and zeros. So we have, in this case, we have a 0 at 0 and we have a pole at A. It might be through the delay theorem that we'll be getting into that we might not have a pole or a 0 visible on the Z-plane, in which case it's going to be out there at infinity. It's not going to be not present. It's always going to be present, but it might not be something that you plot. So when we get into these special occasions, you have to put a note on your z-plane plot, x at infinity or 0 at infinity, just to understand that they are there. I don't, has Dr. Trimboli talked about that already in controls? I'm just curious.
No, I'm familiar with it from 2610.
Okay. So 2610 or always at equilibrium? Did everybody else learn that about the equilibrium, poles and zeros, balancing? It's useful because it's like another check. You know, is everything present and accounted for? So now what we're going to do is reverse this sequence, have the exponential sequence run backwards. So minus a to the n u of minus n minus 1. So this is a sequence that's going to run backwards. My computer seems to be struggling today. You can't tell, but it's lagging. So I'm drawing, and it's not always drawing with me. It's kind of falling behind. So this is a left-sided sequence. This is not something you think of as being real-time or causal at all, but the mathematics allow for this, and DSP allows for it because we want to be able to handle signals that are anti-causal and causal with respect to the idea that we might be post-processing or doing something non-real-time. We have a bunch of data. We're going to do some processing on it after it's been captured. So we take and evaluate the z-transform of this sum, taking into account the definition of u of minus n minus 1. That's going to be a step function that starts at minus infinity and turns off at n is equal to minus 1. So that's what I've done in here. I've just redone the index, and now what I want to do is I want to re-index that sum. So I'm going to change variables. I'm going to flip the sign on n in the sum index, and then I'm going to change the order in the summing. Remember, when I change the order in the summing, I can just change the sum index around without getting a minus sign or anything. So what I'm going to do is I'm going to let, that's going to go to plus 1. I could let that be m. That's going to be infinity. So minus n becomes m. So now I'm summing from infinity down to plus 1, a to the minus m, z to the m. And in my second line here, I didn't change the variable from n to m. In my mind, I just said I'm going to let n become minus n. But I did change the sum, upper and lower sum indices, because I know a sum from infinity down to plus 1 or a sum from 1 up to infinity is identical, right? You're adding numbers, nothing changes. So I'm going to sum from 1 to infinity, and I'm going to have a to the minus n times z to the n, group that together, a to the minus 1 times z, all raised to the nth power. And then I do one additional trick. In my original sum, summing from 1 to n, I'd rather that sum start at 0 because I know how to sum that series. I know it's 1 over 1 minus the ratio. So I'm going to start that series at 0, but then I recognize if I start at 0, I have this term that I'm going to be counting that I shouldn't be counting. So I have a to the minus 1z is equal to 1. So inside this sum right here, there's a 1, a minus 1 actually, because of the minus sign, that was not in the term on the left. So I add a plus 1 to counterbalance it, to just make sure I annihilate it, get rid of it. Is that good? You can do this any way you want to, but I always like to gravitate towards a form in the sum that I'm familiar with, and that is the standard form. Sum from 0 to infinity of r to the n sums up to 1 over 1 minus r for magnitude of r less than 1. So I carry that through, and now I just focus on what that is, and that sums up to 1 over 1 minus the quantity a to the minus 1 times z. Then I can rearrange that as needed, but initially I just plug it in right down here. And then I put things over a common denominator, and lo and behold, I end up with the exact same z transform I had up above. And if you're doing this for the first time, you have to blink and say, am I seeing this correctly? Is there something I'm missing? You're seeing correctly. It is the identical z transform, but the region of convergence, is now flipped. Rather than being the exterior of a circle of magnitude A, it's now the interior of a circle of magnitude A. So that's what's making the right-sided sequence, when converted to a left-sided sequence, which is what this is known as, a left-sided signal. Z transform's identical. The region of convergence is the complement. Or not really the complement, because we can't include the radius of A, but it's the interior of the circle of radius A rather than the exterior. Poles and zeros are identical. It's just now the interior. So this is also intended to drive home the reality that x of z is not unique without knowledge of the region of convergence. So when you do the homework problems in Chapter 3, although they may seem mundane, many of them, region of convergence is required, and I'm looking for it when I grade. I'm going to be zapping a point off at least if I don't see a region of convergence, because that's what makes it unique. And you're saying to yourself, in 2610 and in 3205, I never had to do that. Well, it's because in this class we're doing the bilateral z transform, and we're accounting for the fact that we could have two-sided sequences, and the only way to track that in the z domain is through the region of convergence. So it's a necessary ingredient. So rather than stretch longer, I'm going to take the break right now. We'll come back and we'll combine two exponential sequences together, and then just have more discussions and keep pressing onward so we can get to the inverse z transform here. So right now that clock says it's 9:30. My watch says it's 9:29. So be back here at 9:45. We'll be good to go. I'm going to pause the video. Okay, I've got the recorder back running again to capture the lecture. We're going to visit this next problem, and then we can go take a look at it over in Python if we want to too. There's not going to be a lot of amazing things you can do in Python, but there are some really nice inverse Z transform tools available to check your work, which is the harder part mostly. There's two types of problems in the homework, set number 3. There's forward transform exercises, and then there's inverse transform exercises, and just getting familiar with the tools that are available. So to do this two right-sided sequences example, we can just use this transform pair that's effectively already been developed. We just went through an example of a to the n u of n, and we know that if it's a right-sided sequence, we get this blue boxed result, and now we can just use linearity, which states this for z transforms, and we have to just be really aware of how do we define the region of convergence. So it has to be defined as the intersection of the individual ROCs. And that's all there is to it. So we just take the two z transforms, slap them down on the next to x of z there, and then we have to come up with the region of convergence, and we can directly, notice that we have these two regions of convergence, and in terms of what that radius is going to be, it's going to be the maximum of the two, 1/2 and 1/3. So 1/2 is the winner. And then my preference and my desire when you're working homework problems and exam problems all the way through is to put things over a common denominator. So finish the job. You can start by writing it over negative powers of z. So probably what I would do if I was doing this is I would say, okay, I know it's going to be 1 minus 1/2 z to the minus 1, 1 plus 1/3 z to the minus 1, and then I would have, in this case, I'd have 1 plus 1/3 plus 1 minus 1/2 z to the minus 1. I mean, I just did cross multiplying to get things over a common denominator, and then I would combine terms together. So, the next step would be to take it down to here. And then when I went down to here, I did multiply top and bottom by z squared each to get things in positive powers of z. Why positive powers of z? Because we're more adept, at least I am, at seeing where the roots lie. When I see a z in the top, I know that's a 0 at 0. And if I see a z minus 12 in the top, I know I have a 0 also at z is equal to 1/12, right? And down below here, I have a 0 at z is equal to minus 1/3, a pole, and then a pole equal to 1/2. So I can identify where the poles and zeros are right away. And then if I plot that in the z domain, that's what I've got, is pole 0 plot that shows 2 poles and 2 zeros. In this configuration, it's causal, and we learn that causal sequences have regions of convergence that are the exterior of the largest pole radius, which in this case is 1/2, and again includes the unit circle. It's got a lot of nice things going for it. We could take this example and put one sequence to be a negative sequence, or left-sided sequence, and one a right-sided sequence. And then we could use the results from the earlier example, one just before the break, to have the left-sided sequence, which is down here, I say that and the pen is not working. And then to combine those together, we have the exact same form that we did before, except the region of convergence is going to be the intersection between magnitude of z greater than 1/2 and magnitude of z less than 1/2. So 1/3 is smaller than 1/2. So in this case, we get an annular region that runs between 1/3 and 1/2. What happens if things were flipped the other way? The 1/2 was the left-sided, or right side, the 1/3 was the right-sided sequence, and the 1/2 was the left-sided sequence. Did I say that right? Now, 1/3 is the exterior. So it'd be, I'm making it sound confusing. So if you try to intersect the exterior of a circle of radius 1/2 with the interior of a circle of radius 1/3, what do we get? The empty set, right? There's no points in common. So if that was the case, then we wouldn't have a z transform that exists. We can't write it down like this. We can write down the ratio of polynomials in z, but we don't have a region of convergence that's not empty, so it doesn't exist. Just the way the math is working out here. Any questions on that? I'm working towards sort of a little quiz scenario here of just testing your understanding of regions of convergence here, but I'm not quite there yet. A little bit further. So interesting thing about finite length sequences is they will converge everywhere with the exception of 0 or infinity, possible exception of 0 or infinity. So if we think of, this is the generic sequence, and n1 and n2 are values positive or negative, as long as the z transform is composed of only negative powers of z, then we just can't have the region of convergence include 0, because if we try to put 0 in for any negative power of z, we're going to get 1/0, and we're going to get an unbounded result. And if the sequence is on the left side of the integer axis, so it only contains positive powers of z, then we have those positive powers of z going to infinity if we take the region of convergence out to infinity, so we have to exclude infinity. So that would be, this scenario. And then the first one I talked about, it would be this scenario. So it's the entire region of convergence in one case except infinity or 0, or if you have both negative and positive powers of z, then you just have to exclude 0 and infinity. And these are hard to denote in a picture. If I can get this thing to cooperate with me. Maybe you just have to put notes on the top of it. Drawing the picture is not quite as useful as it is in specific cases where you have finite zeros and poles. But in this, with a finite duration sequence, you have something like this going on. You will have poles at infinity and 0, so I haven't really shown those. So you end up either having This pen it's not working. It will stay connected for a fraction of a second and then it's gone again. Trying to think, how old is this computer? It's about 3 years old, so if I was not retiring from the UCCS, I'd get a new computer in the spring, I think, according to the recycling process. And Dr. Platt and Dr. Tromboli and I have the same computers. I don't know if you notice what they use, but they look identical. I'm the one that spec'd them, and then they said, oh, we like what you're buying, and they bought exactly what I bought. So what we're signifying here when we have strictly positive powers of z or negative powers of z, we're signifying that we either have some poles stacking up at z is equal to 0, which doesn't allow the ROC to exist there, or we have some poles stacking up at infinity. When I say stacking up, it's because that's the type of thing we'll have. We'll have multiple poles and multiple zeros. So I'm going to take a case in point, but I'm going to kind of slide into it with this next example, which I was forgetting about before I get to some general results. So we have a finite sequence, a rectangular window, and this will be an a to the n type window, or it could be a is equal to 1, in which case it's just a rectangular window. It runs between 0 and n minus 1, so there's n points to the window. Let's plug that into the geometric series. Some formula for the z transform. It's like touching the screen makes it disconnect. Every time I put it down, I can see when I'm at a distance. Before I actually touch it, I have the little cursor there that you see. As soon as I touch the screen, then zing, it's gone, it disconnects. At any rate, this has a finite limit. It doesn't go all the way up to infinity. It stops at n minus 1. So we just shift gears and say, okay, we're a finite geometric series. So we know that will be 1 minus the ratio to 1 plus the upper sum limit. So n minus 1 becomes n. That's over here. And then 1 minus the ratio in the denominator. And then if we multiply through by positive powers of z, we can start to see how the zeros and poles are unfolding. It's not totally clear, but we can see that there's at least n minus 1 poles at z is equal to 0. There is at least 1 pole at z is equal to a. And there's going to be n poles from that z to the n minus a to the n. But we have to go into a little study of the roots of unity here to get that dealt with. So you see there's, I guess, 3 different types of pole and zeros identifiable from x of z. There's the single pole, there's the n minus 1 poles at z is equal to 0, and then there's going to be n poles in the numerator. But I'm telling you right now, there's going to be an annihilation going on in here. Annihilation is the word that I like to use when a pole cancels a 0. Maybe that doesn't sound like a good term. It sounds like a military term, right? Annihilating somebody. At any rate, we have to first zoom in on this. This is a good thing to get behind us. And it shows up in the homework problems too. What is it when we have this special type of polynomial? And this is, we're wanting to find the roots of z to the n minus a to the n, is what we're trying to do. So that is the form of those roots. The roots of unity is what it's called. In general, here it's the roots of a to the n. So what we're looking at is z to the n being equal to a to the n. So what values of z will do that for us? And it's the zk equals a e to the j 2 pi k over n that will do it. So the roots can be anywhere on a circle of radius a as long as their angle to the real axis is 2 pi k over n, because when you raise that to the nth power, that just becomes a to the n, because n times that exponent e to the j 2 pi k over n becomes e to the j 2 pi k when the n multiplies through. So that's sitting at z is equal to 1, or it's sitting at 1 in the complex plane. And I know you've seen roots of unity before, but you probably, those fade away if you don't use them. But the idea that you're going to get a whole collection of roots out of this. It's an nth order polynomial, and it will have, in general, n roots. So the roots here are 0, k is equal to 0 up to n minus 1. So they're just roots around the unit circle. So they sit, in this case, well, I shouldn't use poles like that. I should just, well, the angle, the smallest angle is two pi over n on a circle of radius a. So this is the picture of the configuration that we have in the final form. There is a pole at z is equal to a, and there's also a 0 at z is equal to a from that roots of unity, and those are the ones that annihilate each other. So there's no pole or 0 sitting there at z is equal to a. And then there's n minus 1 poles sitting at z is equal to 0, and then the rest of the poles are sitting around on the unit circle, or I mean on the circle of radius a. If we make a is equal to 1, then the circle has radius a, or radius 1, I mean. If I had a Jupyter notebook, or I mean a Pluto notebook open, I would have an animation of that, but I don't have that open. I have another slider control, but I don't have that one open. I don't think I necessarily need to get into that. You trust me that with Pluto I could have animation, I could move parameters around and watch it move. I'll maybe do more of that one day, another day. But instead I can do it statically in Python pretty readily too. So I can back up here as a basic starting point. I can just take a to the n u of n, and I just see what the z transform is, 1 over 1 minus a z to the minus 1. And I have this function that I've defined called z-plane, which will plot the pole 0 plot for a z transform, or some signal that I have the numerator coefficients b and the denominator coefficients a. So I put those in as arrays into b and a. There's some other features in here. It will detect, it'll auto scale. You can change the radius manually if you want to. and then by default I try to detect repeated roots with a tolerance of 0.001. So that means if two roots are, you know, like right on top of each other within a magnitude of 0.001, they'll become counted as one root, and then I put a little number next to it telling you how many times it's repeated. Sound good? It's a cool feature. I worked an awful lot when I wrote this code to make that work, and it's a little bit dicey. I mean, it was a good workout in writing code and getting in numerical algorithms to work. This comes into play, though, in the second homework problem, and I'm going to talk about that here before we leave today. So at any rate, when I run z-plane on that, I can just, you know, get the pole 0 plot. If I change the location of the pole to 0.8, now you see it move to the inside, and we have a single 0 sitting right at z is equal to 0. If I just put some numbers up into the numerator, like this is a finite length sequence, and it starts at 0, I have 1, 2, 3, 4, and those roots, those zeros are sitting outside the unit circle. I know if I reverse the order of the polynomial, and we're going to learn more about this in another chapter, but this is a way of flipping the roots of the polynomial so they're now inside. See that they're now inside the unit circle. I feel like I'm a magician doing a magic trick or something. I just know that this is true. It's just a polynomial property. Do you get excited about polynomials? Maybe yes, maybe no. You learned about them in calculus a long time ago. Polynomials show up a lot in signals and systems theory, and knowing what the roots of polynomials are doing is something that you kind of get more of a knack for the more you do this sort of stuff. And whether it be control systems, feedback and control, moving poles and zeros around when gains change in things, or in filters, or in tracking loops, in signal processing that I deal with, which is like feedback and control. There's this connection between polynomials and roots, and then signals or systems and pole and zero locations. To me, the pole 0 plot is kind of a fascinating visual of what's going on and making a system tick when the poles and zeros are taking on different locations. And in this case, to balance, this polynomial has 4 coefficients. So how many roots does a 4 coefficient polynomial have? It has 3, right? Because you just think of the quadratic. It has a constant first degree term and then the second degree term. So the number of roots is always 1 less than the number of coefficients. So we have 3 roots, and because we don't have any coefficients in the denominator, we have to have 3 poles to balance that, and we have 3 poles at 0. Now we can go ahead and do the rectangular window and just carry that out a little bit further. So we have n is equal to 10 in this example. I've got a is equal to 1, and do a stem function plot. And you might notice in Python, at least, I mean in Julia I wrote my own routine to do this, do it differently, but about 3 years ago in Python, the version that we were using complained if you didn't add in this third option, use line collection equals true. Now they've updated it and it's not a requirement anymore, but I just haven't cleared it out of a lot of the notebooks, and this one is the one I reposted yesterday. So it's the speed at which it does the graphics. It's supposed to be different, and I think it's faster to leave it in, but I'm confused. It's the writers of Matplotlib that could tell me the answer to that. And when I used to go to the SciPy conference, you would get a chance to meet all the maintainers of the various libraries, and I would ask them questions. about that, and they would tell me the answer. You'll also see sometimes when I'm doing plots in Python, at least Julia is different, but you'll see me throw this at the end, tight layout. If you're doing a multiple plots thing, the two plots may end up overlapping each other. If the last line in your cell is tight layout, it lays things out so nothing touches and all the labels are visible. I picked that up at a, what do they call that again at these conferences when developers get together? They call it a birds of a feather session. Has anybody ever heard that term before? You go to a conference, a birds of a feather session is where people who have the same interest will go to this meeting of these developers and other engineering types, and they will just talk about things that are their hot topics, and then another group of people will go to their session because it's going to be, they have a common interest. So I went to the Matplotlib birds of a feather session because I had some things that I was frustrated about and wanted to understand better, and sure enough, they start using this tight layout function all over the place and some examples they're giving us, and I say, so what's that all about? And they said, it's to do this, and it's to make the plot look nicer at the end. It just sort of cleans it up. So in this case, we don't need a tight layout, but if I was doing these as subplots, I would need a tight layout because the two plots would lie on top of each other. And I think probably when I wrote this, I didn't know about tight layout, so I did it as two separate plots. I created a new figure. I created a figure of size 6 inches wide by 2 inches tall, and then I created another figure of 6 inches wide by 3 inches tall, rather than using subplots. But now I would solve that problem by using tight layout or something. I don't know. Just things that can be helpful. At any rate, you see the 10 samples, and here you see n-1 poles at 0, and then you see 9 poles or zeros all the way around on the unit circle, and of course here you never see anything because this is where the pole and the 0 canceled. I mean, I didn't go back to look at this again, but when we put all of this together, there is a 0 at z is equal to a and this up above, so those two cancel. And let's see, what's really positive about that is the fact that there's n total coefficients in this function, and it's all in the numerator. So if you think about taking the z transform, there's just n total terms in the numerator, so there's a polynomial of n-1 degreed polynomial. So there's going to be n-1 roots in this, and that's what we're left with. We end up with n-1 zeros, and then we end up with n-1 poles, and everything is happy. I mean, it's balancing the size of the length of the polynomial. It contains n coefficients, but it only is of order n-1 because that's the way polynomials work. And over here in the simulation or the numerical stuff, everything's happy in the end. Things like this, though, are things that you gotta learn to be looking for. It's like if I'm not seeing what I expect or something doesn't seem right, the numerical thing here should work properly. Sometimes if the math that's going on in the background is brought in a particular way, you might see a pole or a 0 on top of itself, in which case it's the way the factoring was done and they didn't get canceled out. Guess what? Our brains are better than computers are. We can see what needs to be canceled. Sometimes the computer, because of its numerical precision, doesn't get that figured out. So put in A is equal to 0.9, and we see it's exponentially decaying, and now we see that the roots pull into the inside. I also go ahead and plot here the frequency response, or the spectrum, since in this case, and in both cases actually, I can take this configuration of poles and zeros and I can enter that into, I can enter in just the signal into the numerator in freq z, and I can get the frequency response. So this is the decaying exponential finite window, and we know if we put A back equal to 1 again, it's like the moving average filter that we studied before. And now if I run the frequency response, it's going to have the sharp zeros at multiples of the underlying period or frequency, harmonic frequency of placement of these zeros. And now that we have the z-plane, we can get the added bonus that we know why those sharp nulls are there. It's because e to the j omega moves around on the unit circle, and that's the frequency response, right, or the spectrum, or the frequency response. So when the frequency gets up to 2 pi over 10, that is where we have a 0, and that's right there. You see that? And then the second one occurs here at 0.2, and then so on as we move all the way around the unit circle. Every time we hit a 0, it's like our tent. We have a tent stake, so we're tied down to 0 as we sweep around on the unit circle to see what the frequency response is. And yes, there's poles at 0, but we're nowhere near them, so we've got a superpole of 9th degree or whatever that's, you know, flying up to infinity with a power of 9, but we're never near it. We'll see a picture of that in a later chapter. If I was to draw the three-dimensional surface of what we see right now, this looks like a, since you have to chop the plot off not at infinity but at some large number, it looks like a tree trunk that is just shooting up to infinity because of the poles at 0. And then around the tree trunk there are gopher holes, is what I call them. Those are where all the zeros are occurring. I mean, this is my analogy, and I have ponderosa trees in my backyard, and there's little moles that like to dig holes at the trunk of the tree. Take your pick of the rodent you want to pick on, but you can say that's defining a 0. We'll see a picture of that later, but a visual of what's going on now. And the fact that it's a moving average filter, another really cool aspect that we'll study more later, but I'm just going to point out now, is the fact that the pole 0 cancellation that occurs at z is equal to 1 or omega equals 0 makes this a low-pass type filter because it does pass DC and it's averaging in the neighborhood. What's wrong right now is I'm not dividing. If I wanted to make this a moving average filter, I'd have to divide by 10, in which case then I'd be averaging, so I'd have a unity gain, but I didn't do that initially. But the idea is it is a low-pass filter, and that's what a moving average filter is too. Okay, inverse Z transforms is the next thing I want to talk about in numerics, but we have to look at a few properties of the ROC first. Are there any questions, though? I've been whizzing away here, and you can see I've done this too many times. My brain just starts firing. This is cool to see this relationship. This is cool to see that relationship. You're going to have to slowly get your brain cranking away on all these relationships, but they're all wonderful. I mean, that's what makes your understanding rich when you finally see all these connections. And I can't reproduce that because I've done it too many years now. I can't think back to strip away all the things. And I honestly think there's more things out there that I still haven't realized yet. I mean, you've learned different topics, don't you? feel like there's always still more, another relationship that if you just study it some more at a slightly different angle, all of a sudden, oh, I never realized that either. I guess something over here in MATLAB, or not MATLAB, but in Python or Julia that I didn't mention is that to try to give an example of a sequence that's running negative is a lot more challenging, but it can be done. I mean, it just involves shifting and playing different games, and I don't want to do that until I have some theorems to do that. There's a time delay theorem. And of course, the other thing is this does not show the region of convergence, so you have to still be able to understand, is it left-sided, is it right-sided, what is the region of convergence. Here, everything that I'm doing in Python is assumed to be a right-sided sequence, so the regions of convergence are always going to be at the largest pole radius. It's just the way that will work out. And just give you an example of craziness that we're going to eventually get to. I had this as 1, 2, 3, 4. If I make the denominator be 4, 3, 2, 1, I now have poles on the inside and zeros on the outside, and these poles and zeros are at conjugate reciprocal locations, so that if I was to do the frequency response of this filter, let me just snag that cell, copy it, paste it in right there, and put in that for my A and B. I get a real exciting frequency response or spectrum, which is what? Perfectly flat. This we're going to learn about later. It's called an all-pass filter. When we have conjugate reciprocal poles and zeros, we get an all-pass filter. It does have a phase, though, that is controlled, and it's a wiggly shape depending upon how these poles and zeros are set up. But we'll also learn that if we reverse the coefficients between the denominator and numerator, that's a way of making an nth degree all-pass filter. We'll get to that later, though. I thought you might find that interesting right now. Okay, properties of the region of convergence. Property 1, it's always going to be an annulus centered at the origin, where you have radii r sub r and r sub l controlling the region of convergence. We said that earlier. That's not a startling result. The Fourier transform, though, of the sequence converges absolutely if and only if, so this is a nice theorem, if and only if the region of convergence includes the unit circle. So whenever you see unit circle in the region of convergence, you know you have this, either the Fourier transform exists or the system is stable because of the fact that the Fourier transform exists. Property 3, this kind of is an obvious one. Region of convergence cannot contain any poles, because a pole is just like I've been telling you, it's like in a tent that's going up to infinity, and you cannot sit at infinity and have the existence of a converged Z transform. So you have to stay away from the poles. If you have a finite duration sequence, property 4 says you have the entire Z-plane except possibly 0 and infinity. And actually, there's only one sequence that includes the entire Z-plane, and that is delta of n, because delta of n is sitting right at 0, so in its z transform it does not have either a negative power z or a positive power z to cause it to diverge. It's not a very exciting z transform though, so the z transform of delta of n is simply 1 everywhere. And that's like, duh, I could have told you that. 1 doesn't have anything exciting happening in the z domain, it's just a constant everywhere. Okay, these next couple are the really cool ones, the ones that we carry around a lot. If the sequence is purely right-sided, and right-sided means that it's 0 starting at some value of n, which could be negative, but still it's a starting point, and it can go all the way up to infinity. So it starts at some point either to the left or right of 0, but then takes off going to the right. Then we know that the region of convergence is always the exterior of a circle, and this is the important part here. Oops, get this selected. Why is it not working? It's not working. I used to be able to draw with the mouse, now I can't. I'll do that. Okay, it corresponds to the largest pole radius. So that's going to happen for right-sided sequences. And if you expand using, if you have to do partial fraction expansion because the roots are not all simple but are complex conjugates, it's still going to be the maximum pole radius, whether it's a complex conjugate scenario or just a simple root. So I say that in the very end. If it's a left-sided sequence, so it starts at some point either to the right of n is equal to 0 or to the left, but then goes backwards towards minus infinity, that's the definition of a left-sided sequence, then we have the same result as we do for property 5, except that the region of convergence is now the interior of a circle corresponding to the smallest pole radius. And if you have a two-sided sequence, then it's just a combination of left and right-sided sequences, and the region of convergence will be the intersection of the largest pole radius corresponding to the right-sided and the smallest pole radius corresponding to the left-sided, and that will then, if it exists, form an annular region. Last property, connected region, which I said a long time ago, is just an obvious thing. You can't have two annular regions and say, I want to claim convergence in this annulus and this annulus, because that violates the definition. So, yeah, I got 10 minutes left. I wanted to get to the inverse Z transform. I'm pretty close, but I want to go through this little discussion to see if you're following regions of convergence. Suppose I have three poles, and I want to consider what type of configurations I can make out of these three poles in terms of left and right-sided, and what are the valid regions of convergence. So here's two of the valid regions of convergence. One is the exterior of the pole at C, and the other is the interior of the pole at A. So if the first one on the left is the region of convergence, what is the nature of the sequences corresponding to pole A, pole B, and pole C? Just checking on what we just went through. And what I say situation, I'm saying left or right-sided. So if C is setting the region of convergence, are all those right? Are some of them left? And so on and so forth. So what must be true? So they're all right-sided, right? Because it's the largest pole radius, and that's setting the region of convergence. So the second case is left-sided, because it's the smallest pole radius. So then these are the other two valid regions, the annular region between A and B. So think about this for a second. What's the configuration here? What's left and what's right? A has to be a right-sided because it's outside of it, right? And B and C, what are they? Since the minimum pole radius gets set for left-sided sequences, it must be that B and C are both left. So it's the smaller of the two, and then the intersection is what we have for the annular. So we go to this last case, and we have the annular region between B and C. So C has got to be left-sided because it's coming to the inside of that, and then A and B have to be right-sided, with B being the larger of the two. It's like a new language of looking at a picture and saying what's behind all of this. But it's kind of an engineering type scenario always is taking a problem and turning it inside out, looking at it front and back, top and bottom, and all that other good kind of things. Last little thing is stability, causality in the region of convergence. So we have a pole zero plot that shows two zeros at 0 and a pole at -2 and a pole at 1/2. So to make this system stable, how does the region of convergence have to be configured for this system? To be stable, which means that the Fourier transform exists, which means that the region of convergence includes the unit circle. What has to be going on here? We have to have the pole at 1/2 being right-sided, and the pole at -2 has to be left-sided, so that we have the annular region. I don't think I drew a picture of it here. No, I just put it all in words. So we can have a stable system if we have a right-sided and a left-sided. It's not going to be a causal system, but we can do it just the same. We'll talk a little bit about how to make a non-causal system causal in a minimum phase sense. There's some other really cool things to talk about, obviously, that I haven't had a chance to get into. If this is a stable system, then both poles have to be right-sided. I mean, it's a causal system, then both poles are right-sided, and it's going to be the exterior of a circle of radius 2, which is not going to be stable. So these things are kind of all written out down here. And I'm looking at the clock. I do want to talk about partial fraction expansion, but I want to give you a hint on the second homework problem to help you do some fun stuff. There's some more things to talk about in here. There's tables, and then there's going to be going into partial fraction expansion. And that is nice and easygoing. If you're going to get into working the homework problems, I'll just point out that we always want to work with negative powers of z. So I think I have this function shown as having negative powers. Well, no, this doesn't, yeah, up here. So just one thing I want to say. When you do partial fraction expansions, and that is the way this table is set up, do not try to switch to positive powers of z. Do not try to go like you did in the S domain, which was always positive powers of s, and try to create some combination of the two. You're just going to get very confused and very messed up. So stick with that. Assuming you want to check your work, though, you will have this nice capability over here. Residue z is available through scipy.signal, and with it you can do negative powers of z, and it will get your partial fraction expansion figured out, and I go through examples right here on how to do that. I'm not going to do it because I'm out of time. I want to give you a hint instead on a homework problem. But as you start moving along on this, definitely look at this notebook. And if you don't want to download the notebook, I have the PDF rendering of it right on the website too, so you can see how you can check your work, and that's how I've worked the homework problems. Meanwhile, with a teeny bit of time that's left, I want to talk a little bit about one problem. I wish this worked better for me. Okay. Actually, first comment is when you're working problem 3.3, I want you to work A and C. A is a two-sided exponential. That's separate, but B, which isn't assigned, is related to part C. So in C, though, the signal is C is right. It's a triangle-shaped function, and I'll be putting out a hints page, but I just thought I'd bring this guy up because part B just says find the z-transform of the rectangular pulse shape, which is pretty much what we've already done in class today. We were doing the finite geometric series and so on. But now it says find the z-transform of this triangle. And what I want you to consider, though, is that you can look at it as the convolution of two rectangles. So we haven't gotten to the theorem yet, but we are going to get to the theorem that says that the z-transform of say x1 of n convolved with x2 of n is the product of their z transforms. And so this problem really becomes very simple if you just take what we've already done today with the rectangular window, in other words, A equaling 1, and then convolving it with itself to get the z transform. And you just want to be able to prove that what I've set up here is going to be correct in terms of convolution. In other words, when you convolve a sequence of duration n minus 1 with another one of n minus 1, it's going to reach its peak when they overlap completely, and that will give you the peak at n minus 1, and then the last non-zero point is going to be at n minus 2 as one is sliding past the other, and that's going to represent what is in the problem description for part C. And you're going to get a result that you can then create a picture of if you want to too, and you'll see double pole or double zeros everywhere and things like that. You can model it in Python if you want to. Let me just give you a quick little tour of something that I was just thinking of here, which will be interesting. I can multiply things together. I can convolve things directly if I just do, suppose I do 1, 1, 1, 1. Okay, that's just convolving the two sequences like I was just talking about. Notice that I'm getting a triangle shape, and if I go ahead and put that in z-plane, let's see, I messed something up in here. Signal convolve. Oh, I've got to put this in front of it. And I probably need to change the size here to something else. There we go. So notice everything's got double 2's on it, and there's 6 down here. You have to think about that, but that's kind of to be expected, because if you're taking one x of z times another x of z, wherever there were poles and zeros, you're going to just be doubling everything, right? Where you have a z, you're going to have a z squared, and so on and so forth. So it's kind of cool the way that works out. And you don't have to invent a new z transform. You can just use a theorem to get there rather than having to mathematically go ahead and take this blue guy and write that out, which is not going to be summable using the standard geometric series. You'd have to use an arithmetic geometric series for that, which is in my crib sheet, by the way. You could get it from that place if you wanted to. Just go back over there really fast. Lecture notes, crib sheet. You'd end up having to use this one, I think, k times a to the k, and then you'd let the a equal 1, but you'd be summing from 0 to n of k, and then you get something like this. That's the arithmetic geometric series. That'd be another way of getting it. And you can well, I won't say anything more. I'll let you fumble around with that. What I just showed you is the best way to go, though. If not, you have to kind of get more creative with it, and you'll have to go to another series sum formula. It still involves geometric, but it's not the pure geometric series sum formula. I will get the hints page out, though, and we'll see where we end up with next Tuesday. But the plan will be to have exam 1 2 weeks from today. I'm still feeling good about that.